Okay, so let's start. Today I'm going to talk about the weekly problem set 5. So let's get started. For the first problem, consider a permutation of set n, and then the first problem is to prove that the G prime, so a permutation is a collection of disjoint cycles if we represent the permutation pi with a directed graph. And so the first problem, we have to prove that G pi is a collection of disjoint cycles. So the way we prove that is, so if you, since we only have a finite set of vertices and every permutation is a one-to-one function, then since it is a one-to-one function, then every vertex should have exactly one edge going out and one edge going in, right? Since it is a one-to-one function, then if we start, for example, at here, if we start at an arbitrary vertex and we go on traversing this cycle on and on, like continuously traversing this cycle, at the end, since it is a finite set of vertices, we will go back to here. So if we start at a vertex x, and we, for example, this is A and this is B, and we continue going on, at the end, we will go back to x. So we will go back to vertex, so we will visit a vertex x twice. So this is the vertex that we will visit twice. If for example, this vertex x, the first vertex that we visit twice is not the vertex that we start traversing the cycle, then for example, maybe the first vertex that we visit twice is A. So we go back here. Then you can see that for this vertex A, we have two incoming edges. Then it is one-to-one function. So it is not allowed. So we must have an edge that is going. The first vertex that we visit twice must be an edge. Must be a vertex that we start at the beginning. So this is a cycle. Then why is it disjoint? It is disjoint because since suppose this permutation is not disjoint, then we may have, for example, this two cycle, and we have a vertex that belongs to both cycles. Then this vertex has like multiple incoming edges or outgoing edges, and it is also not a definition of one-to-one function, so it must be disjoint. So every permutation is a collection of disjoint cycle. For the second problem, we have to prove that there is an integer k such that if we apply permutation, if we apply the permutation pi repeatedly for k times, so let's consider this graph. So there is an integer k. Suppose that we apply this permutation. So permutation of 6. So we apply the permutation and we go to 1, and then we continue. We go to 5, and then 8, 12, 9, and then finally we go back to 6. And this integer is so 1, 2, 3, 4, 5, 6, 7, 8 times. So we traversing this. So this cycle has 8 vertices. So we this integer k for this cycle is 8, and for this one is 1, is obvious, and this one is 3. So there is an integer k such that if we apply this permutation pi repeatedly for k times, and every element will return to its original position. So it's like this. So we start at 6 and we start at 3 and 2. So we continue applying the permutation for all these cycle. Like you can observe that after 24 times, since 24 is the least common multiple of 3, 8, and 1. So after 24 times, the permutation of this cycle will go back to its original vertex, and it will also go back to its original vertex. So there exists a k such that this permutation, if we apply it for k times, then all the elements will go back to original position. So this is for problem 2. And then for problem 3, we can easily follow from problem 2 that we just need to start at a vertex here. So we arbitrarily from this graph, we arbitrarily choose a vertex, and then we start traversing this cycle. And then after we go back to its original position, we record this number, so it's 8. And then we go on to another visited vertex. So we may pick vertices from these 4 vertices. So let's say if I pick 3, and then I traverse cycle, I found that the number k for this cycle is 3, and for this one is 1. So in the end, we just need to find the least common multiple of all these disjoint cycles, and we will have the smallest such k. So this is the algorithm for this problem. Okay, for problem 2, we say that a permutation on a set n is a swap if there are 2 indices I, which is not equal to j, such that its permutation I is equal to j, and then permutation of j is equal to I. And for all the other elements, it remains the same in its original position. And we say that it's a simple swap if j is the next element of I. So for the first problem, we have to prove that any permutation is a finite composition of swaps. So we can so after finite number of swaps, we can reach from the original set n, which is sorted permutation. So the initial permutation, and then we can go back to any other permutation in a finite number of swaps. So the way that we prove this is by starting from an arbitrary permutation, and then we can apply a finite number of swaps, and then we can go back to the original sorted order of the permutation. And then since we can go back from any permutation to the original permutation, then we can also reverse this process and obtain any permutation. So consider just like this permutation. We can first find the smallest element, which is 1, and then we want to put it back to the to its original position, right? So we want to put it back here. So we can just do a swap. So it becomes 1, 3, 2, 5, 4. So you can see that now this 1 is in its expected position. We have only 4 elements left to sort, right? And we can just find the next smallest element, which is 2, and then we swap it. So 3, 5, 4. you can see that now 2 goes back to its original position, and 3 it also go back to its original position. So it is not guaranteed to happen, but in this case we are lucky and we get 3 also back to its original position, and then we can just do another swap. Then it go back to this. So since every time we do a swap, we do this kind of swap, we find the smallest element and then we put it back to its position. The number of this unsorted part is decreasing. So you can see now here we only have here we only have 2 unsorted elements. So every time we perform a swap, the number of unsorted vertices it's decreasing. So after a finite sequence of swaps, we can definitely restore it back to the original permutation. So we can reversely, like from the original permutation, we can obtain any other permutation. This is problem 1. And then for problem 2, we have to prove that any permutation is a finite composition of simple swaps. So in problem 1, we proved that it's a finite composition of swaps. So just swap. And for problem 2, we have to prove that it is also a finite composition of simple swaps. To do this, we only need to prove that each swap is a finite composition of simple swaps. Then since each permutation is a finite number of swaps, then each permutation is also a finite number of simple swaps, right? So we just need to prove that a swap is a finite composition of simple swaps. So again, let me use the same example, maybe. Yeah. So suppose that I want to also put 1 back to 5, but this time I can only use simple swap, right? So to do this, you can see that 5 is in the first position, and then 1 is in the 4th position. There are like 3 simple swaps in it, right? So we can first bubble up this 5 to this position. First bubble up this 5 to the 4th position, and then we can bubble down this 1 to its original position. So this sequence of swaps will be, so 5 we switch with, we swap with 3, and then we swap with 2, and then we swap with 1. Right. So you can see we only require 3 simple swaps to put the first element to to its 4th position. So this is actually just let this bigger position be j, and then this smaller position be i. Then we only need j minus I simple swaps to put the ith element to the jth position, right? And then after that, the original jth position elements will be placed in here. So this is j minus 1, and then we want to put it back to I, right? So it only requires 2 simple swaps. So it's the same argument, 2 simple swaps. So this is actually just j minus 1 minus I simple swaps. We can put we can put this 1 back to its original position. So in total, we just require this number of swaps and this number of simple swaps, and we can perform any swap. So we prove finite composition of simple swaps. So every permutation is a finite number of swaps. So every permutation is also a finite number of simple swaps. So this is part 2. And then for part 3, we say that the permutation is even if it can be obtained as a combination of an even number of swaps. And similarly, we say that odd the otherwise. So every permutation is either even or odd, but not both. So given a permutation, it is either be obtained by an even number of swaps or an odd number of swaps. And we have to prove this. So we can use the idea of graph in the first problem. We have already proved that given a permutation is just a disjoint cycles, right? You have proved that in part 1. Every permutation is just a collection of disjoint cycles. So we can write, I just used the example in part 1, problem 1. So this is the permutation, and we have this graph. So if you observe, you can observe that if we do any swaps, so any arbitrary swap, if these two elements is originally in the same cycle, then this cycle will be split. So will be split into 2 cycles. So now, right now, we have 3 cycles, right? This is the first one, second one, and the third one. So we have only 3 cycles. If we change, so if we swap, let me see. If we swap just one, let me arbitrarily take 2 elements, just 1 and 4, right? If we swap these 2, then you can see that the permutation now becomes 4 and 1, right? So the graph will be like we have 7. Oh no, this is 6. We have 6.24. So this vertex should be 4, and then we have 4.25. Let me erase this to 5, and then 5 it's points to 8. So this is a new disjoint cycle. And then let me put 1 here. So 1 will point to 7, and 7 will now point to 1, right? So it's just this, right? So you can see that originally we have 3 cycles, now we have 4 cycles. So this is if the 2 vertices are in the same cycle, but if they are not in the same cycle, let me reverse it. So now, if they are not in the same cycle, for example, if I swap 7 and 3, so 3 and 7, so these 2 vertices are not in the same cycle, we have now 1 will point to vertex 3, 1 to vertex 3, and then this is, we have 12 vertices, right? This is vertex 10, 2, 3, 4. So this is vertex 10. So vertex 10 will point to vertex 7. This is vertex 7, and vertex 7 is pointing to vertex 4, right? Pointing to vertex 4 and not 11. And now we should have another, so vertex 3 is pointing to 11. So it's like this, right? So now it becomes one cycle. So we have 1 and 2. This is a cycle, and this is a cycle. So we have 2 cycles. So it becomes from odd. So each swap, if the 2 elements, the vertex in the graph is in the same cycle, then after the swap, they will become split. They will be splitted and becomes a different. So it will generate one more cycle. So if in the original graph they're in the different cycles, then after the swap, these 2 cycles will be merged, and we have one less cycle. So you can see that after every swap, if we have an odd number of cycles, it will become an even number of cycles. If we have even number of cycles, after the swap, it will become an odd number of cycles. So it changes the parity, right? Every time we do a swap, the number of cycles is changed from an odd number to an even number, or vice versa. So it changes the parity. So each permutation, we can either, if this permutation we have an even number of cycles, we can't obtain it by another, like we can't obtain it by another permutation which only have odd cycles. So every permutation is either even or odd, but not both. So for part 2 or part 4, if n is larger than or equal to 2, we have to prove that the number of even permutations of n is the same as the number of its odd permutations. So let me first define that a simple swap S, it's, so we want to maybe just swap 1 and 2. So this is defined as maybe a permutation. This is defined as a swap. So we keep every other element except for this 2 in the same place, and we swap this 2. So this is a swap, and then we want to create a mapping from the original permutation. We want to map it to this simple swap and composite function with this permutation. So what this means is just after doing this permutation, we further do a swap of 1 and 2. So this is what it means. And you can see that this mapping is 1 to 1 and onto. So both 1 to 1 and onto, since if a particular permutation pi 1 is not equal to pi 2, then this this composite function will also not equal, right? So this is 1 to 1. And onto, it means that every permutation can be expressed as this, right? Since we just, if we want to obtain a permutation, if we want to obtain a permutation, we can just do another permutation, and then we can swap it. We can swap 1 and 2. So if 1 and 2 in the permutation that we want to obtain is not swapped, we can just swap it in this part, and then we have to do another swap here. So we can obtain any permutation with this can be expressed. So we can obtain any permutation with this function, with this composite function. So since this is 1 to 1 and onto mapping between these 2 functions, so it maps every even permutation to an odd permutation. Since if this is a even permutation, then we apply another swap, then it becomes an odd permutation, right? So it also changes the parity. And since this mapping is 1-to-1 and onto, so we have that the number of even permutation is equal to the number of odd permutation. Okay. So this is problem 2. And for problem 3, it actually has a algorithm to solve this, and I will direct you to the reference of this problem, since it is a algorithm that you can find online, and I'm not going to go deep into this part here. But in general, the formula to obtain the number of connected graph on a vertex set n is just, so the Gn is equal to this one. So we have a formula to calculate this. And this one, this part. So this is the, oh, sorry. So this is the formula. So I will give, so the later the distributed solution to have the reference to the algorithm. And to problem 4, let G be a simple graph without even cycles. We have to prove that G is tripartite. So it is equivalent to 3-colorable. So if we can color a graph so if a graph is 3-colorable, it is also tripartite. To do this, I'll first introduce an algorithm. It's called DFS algorithm. So we first initialize a stack S, and then array visited to record every visited vertices, and then we pick maybe let me just go through it with this example. So now we have the array visited here to record that whether we have visited these vertices, and then we have the stack here. So maybe let me just create this DFS tree while doing the DFS algorithm at the same time. So firstly, we randomly pick a vertex and push it to S. Let's say we pick this vertex 1. So we have the first vertex here, and then we push it to S. And then we go to step 3 here. We pop the top element, which is 1, mark it as visited, and we push all of its unvisited neighbors to S. So it's 2 and 3. It's 2 and 3. And then we will go back to step 3. And then we pop the top elements. Let's say the rightmost element is the top. And then we add this, and then we mark it as visited, and we add it to our DFS tree. Right now we're here. So we add this vertex to the DFS tree, and then we mark it as visited, and then we push all of its unvisited neighbors into S. So it's 4 and 5. 4 and 5. So we go back to step 3. We pop the top element, mark it as visited, and we add it to the DFS tree. So right now we're here. We add it to DFS tree, and then we want to push all of its unvisited neighbors to S. But right now we have no unvisited neighbors. Since 4 is already in the stack S, and for vertex 3 we have already visited. So we do nothing at this step, and we go back to step 3. So we go back to step 3. We pop the top element, which is vertex 4. We mark it as visited, and we add it to our DFS tree over here. And we want to push all of its unvisited neighbors to S, but we have no unvisited neighbors now. So we just go back to step 3. and we want to pop the top element. We're at vertex 2. We want to pop the top elements, and then we mark it as visited. And since we go back to this vertex 3 and then back to vertex 2, so this DFS tree, in this DFS tree, the vertex 2 is connected to a vertex 3. So this algorithm terminates since we have already visited all of its vertices, and we have this DFS tree here. So this is the DFS algorithm, and we now have this vertex, have this DFS tree, and you can see that it is a spanning tree of the original graph, right? But there are some edges that is not included in this DFS tree, and for these edges that is already present in the DFS tree, we call it the tree edge. So tree edge is an edge that leads to a previously unvisited vertex. So this occurs like when the DFS is running. This occurs when we visit a vertex that is new to us. And this is the tree edge. And we have some edges called back edges. So you should notice that we have some edges that is not included here. So for example, this vertex is not included. This is a back edge, and also this vertex is not included. So these back edges occurs when we connect. So these edges is an edge that connects this descendant to its ancestor, to one of its ancestor in the DFS tree. And this back edge occurs when we visit vertex neighbors. That is, so when a vertex neighbor is already visited, so you can think when we are at vertex 4, this vertex 3 is already visited. So we have this back edge, and at vertex 2, when we are at vertex 2, 1 is already visited. So we have this back edge. So this back edge occurs when a vertex neighbor is already visited. So this is the back edge. And from this DFS tree, we can try to prove that if G is a simple graph without even cycle, we can prove that it is three-colorable. So let me give another example that is easier for me to illustrate. Let me add some arbitrary vertex. So this is suppose this is a DFS tree that we obtain from some graph, and since we don't have an even cycle, so we should not have a back edge that. So right now in this tree we don't have cycles, right? Since tree we have no cycles, and in this graph, I want to prove that if it has no even cycle, then every one of these vertex in the DFS tree can have at most one back edge if it has no even cycle. So the way we prove this is, suppose we have a vertex that has two back edge. Suppose this is the first back edge, and you can see this is an odd cycle since we can't have even cycle. So the two back edges must be an odd cycle, must form an odd cycle. And this is also an odd cycle. So we have a vertex with two back edges, and they are both. Let me give it a name. So this one is C1, and this one is C2. So we have two cycles that is odd cycle, and we want to prove that each vertex in this DFS tree can have at most one back edge, and if it has no even cycle. So right now we have two odd cycles, but if you consider this cycle, we have another cycle formed here. We have this back edge go back from 1 to 5, and then from 5 to 3 we have another back edge, so we can go to one from 5 to 3, and then through this path we have a cycle of 4. So this is an even cycle. Let's call this C3. So C3 is actually an even cycle. It's an even cycle. So you can see that if we want to, if given a graph, it has no even cycle, we can, for every vertex, we can only have one back edge. If we have two back edge, then we must have an even cycle. So this is the way we prove that every vertex should have at most one back edge. Then if every vertex can only have at most one back edge, we can easily color this graph, like greedily cut. We can just use greedy algorithm to color this graph with 3 color. So let me just use the first level is blue, and then give it red, and then this is another color. So I can arbitrarily color this vertex, color this graph. So it's, yeah. So this is how we prove that every graph with no even cycle, we can color its, so it is 3 colorable if it has no even cycle. And this is the way we prove this. And for problem 5, this is actually covered in the lecture. So I'm just going to refer you to the lecture notes. So it's in lecture 18. You can see this problem. It's exactly the same. And for problem 6, a hypercube QD of dimension D is a graph with 2 to the power of D vertices. So, and one corresponding to each binary sequence of length D. And 2 vertices are neighbors if their corresponding sequences differ in only 1 digit. So you can easily see the illustration in this graph. And for the first part, we want to calculate the number of edges of QD. And this is actually easy to calculate. So for QD, since every vertex in QD has exactly D edges going out, so this is Q1, we have 1 edges going out for each vertex. For Q2, we have 2 edges. And for Q3, we have 3 edges. So every vertex has 3 edges going out, and QD has 2 to the power of D vertex. So this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So we have in total D edges times the number of vertices, which is 2 to the power of D. And since each time we are counting, for each edge, we are counting it twice, right? Because we have 2 vertices connected to this edge, and we are counting it twice. So we have to divide it by 2. And this is the number of edges in QD. This is simple. And for part 2, it is also quite easy. Since by the definition that every Euler a graph is Euler if and only if it's connected, and every vertex has even number of edges. So we can easily deduce that if this D is even, QD is Eulerian. So we can easily deduce that. And for part 3, let me prove using induction. So for part 3, for what values of D does QD contain the Hamiltonian path? And I'm going to claim that when D is larger than or equal to 1, so basically all of these graph has a Hamiltonian path. And I'm going to prove that for D larger than or equal to 1, we have an Hamiltonian graph. And we're going to prove this by induction. So the base case, let me use Q1 as base case. So Q1 is this. So it's very trivial that we have a Hamiltonian path here. So we just start from 0, this vertex to this vertex. It's a Hamiltonian path. And this is for base case. Q1 proved, and then induction. For induction step, I'm going to assume that we have a Hamiltonian path starting at every vertex in Qn. We have Hamiltonian path starting at every vertex of Qn. And then we want to prove that this case is also the same for Q n plus 1. So we first observe that in every, so in Qn plus 1, we have 2 copies of Qn. So from here, we see that when D is just 1, so when so for Qn, it always has 2 copies of Qn minus 1. And so you see that this part is here and here. So we can have 2 copies of Qn minus 1. And for each vertex in Qn minus 1, we connect to its corresponding vertex in another copy. So we connect this to this, and then this to this. And this is Qn minus 1. And then we go from here to here. We also have 2 copies. The first copy is this, and the second copy is this, right? And then we connect the corresponding vertex with an edge, and then go on to this part. So we have 2 copies, and then every edge is connected to its corresponding vertex. So in Qn plus 1, we have 2 copies of Qn. Then by the induction hypothesis, we can start at an arbitrary vertex. Maybe let me not write it. We can start at arbitrary vertex here, and then we traverse. So maybe suppose this is Qn, and this is Qn minus 1. We can traverse every vertex here in the Hamiltonian path since it's an induction hypothesis, we can have a Hamiltonian path in this graph, so we can traverse every edge and visit it exactly once, and then we go to here. And since every vertex in Qn is connected to its corresponding vertex in the other copy here, so after we traverse all of the vertex in this copy, we can take an unvisited edge to an unvisited vertex and to another copy. And then from this vertex, since also by the induction hypothesis, we can have a Hamiltonian path from an arbitrary vertex in this copy too, since this is Qn. So we can also have a Hamiltonian path here, and we can finish traversing this copy. So in all, we can traverse this Qn. So for every vertex we visited exactly once, and we have a Hamiltonian path in this graph too. So we prove this by induction. Okay, so for problem 7, it is actually quite easy, and some of it is already covered in the lecture notes. So for part 1, of course, every maximal matching is not every maximal matching is maximum. So just consider this graph 2, 3, and 4. This is a maximal matching, since it is not a subset of any other matching, right? So this is a maximal matching, but we have another maximum matching containing 2 edges here, which is larger than the maximal, which is larger than this maximal matching. So not every maximal matching is maximum. And for part 2, we can just think of the vertex covered definition and the matching's definition. Since for each edge in a matching, it must be covered by at least one vertex in the vertex cover, as a vertex cover must touch every edge at least one endpoint. So for part 2, if you think of this problem by the definition of vertex cover and its matching, so a vertex cover is a set of vertices that touch every edge at least one endpoint. And since so by this we have every edge in the matching must be touched by at least one vertex in the vertex cover. So the vertex cover must have at least the number of edges in the matching. So we have C larger than M. And for 3, it is also by the same argument, by the definition. If we have a maximum matching N2, which is larger than N1, then there must exist some edges in the maximum matching that is not covered by any vertex in the vertex cover. And by this definition, this vertex cover is a contradiction that it is not a vertex cover. So N2 must be smaller than N1, smaller or equal to N1. Okay. And for this part 4, we actually have it covered in lecture 18. You can see for phonics theorem. So it is in lecture 18. You can I will refer you to the lecture notes. And for problem 8, let a graph G be a connected simple graph, and U and V is in the in this vertex set. The distance between this U and V is defined as the length of the shortest walk from U to W, and the winner index is defined as the sum of the distances between all pairs of vertices. So the sum of the distance between all pairs of vertices. First, in the first part, we want to prove that if H is a connected subgraph of G, here we have an error here. So we must have the same vertex sets. So if H is a connected subgraph with the same vertex sets of G, then this winner index of H is larger than or equal to G. So consider a graph G, and we have some vertex here. Suppose we have suppose this is the shortest distance from vertex U to V. Then consider a subgraph of the same vertex sets of the same vertex sets. Consider this subgraph H, and we may have two situations here. So, and we have other vertices. So we may have two situations here. First situation is that this distance of U and V in the subgraph H is equal to the distance of U and V in the in G. So if this holds, so if the distance of U and V in H is equal to the distance of U and of G in of U and V in G, then so it means that every edge in this walk in H is actually preserved in this subgraph H. So this shortest distance still holds. So this walk is still in this subgraph. So we can have the same distance for U and V in the subgraph. But we have another situation is that suppose some edge in between is not included in this subgraph, then we have so this walk is broken here. So we have this edge is missing here. It's not included in the subgraph. But since this edge is a connected subgraph of G, then we must have another walk from U to V. Since otherwise, if we don't have this walk, then H is not a connected subgraph. So we must have another walk from U to V, and this another walk either have the same length as the original walk here, either has the same length as this walk, or it may have more. It will only have more, have a larger length, since we define that this walk is the shortest walk. Then, if there exists another walk from U to V, then it must be larger than this shortest walk. Otherwise, this walk will not be the shortest. So, in this case, the distance of U and V in H is actually larger than or equal to the distance of U and V in G. So, since for every pair of vertices in the subgraph H, it either has a larger distance or it has the same distance, so the winner index of H is larger than the winner index of G. So this is part 1. Part 2, it asks for what is the minimum and maximum possible value of the winner index of G if G is a connected graph with n vertices. So we can first think of the minimum possible value. So the minimum possible value occurs when every vertex has a distance of 1. So if for every vertex it has a distance of 1, it simply means that it is a connected graph. So like this, a connected graph, every vertex is connected to every other vertex. So for every pair of vertices, its distance is 1. So we have the minimum value of the winner index occurs when G is a complete graph, Kn. So this is K3, and the edges is calculated by since every vertex is connected to every other vertex, so it has n minus. So take this vertex, it is connected to every other n-1 vertices. So the distance between them is 1. So we have for every vertices in N, it is connected to every other vertices and every other n-1 vertices. And for every edge, we calculate it twice. So we have 2 divided by 2. So this is the minimum possible value of the winner index of a complete graph. And the maximum actually occurs when the graph G is simply a path graph. So let me prove that the maximum possible value of the winner index occurs when G is a path graph. Suppose G is a path graph. So let G be a path graph. Then it has only n-1 edges. Suppose we have n vertices. Then we have n-1 edges, right? Since between every 2 vertices, not every 2, between the vertices in between, they have an edge. So we have n-1 edges, and I want to prove that every other graph G will have a smaller winner index than this graph Pn. So I want to prove that this winner index of this graph Pn is larger than every other graph. So since a path graph has only n-1 edges, and it is the minimum number of edges that a graph can have, otherwise it would not be a connected graph, since n-1 is the minimum number of edges we can have for a connected simple graph. And let's consider another graph G. So G must have number of edges larger than the number of edges in Pn. So we must have larger number of edges than Pn. So suppose it only has one more edge than Pn, and I have to put arbitrarily between two vertices in Pn. So suppose like here, actually it has to be larger than or equal to. So let me put this edge here. And you can see for these 2 vertex, originally their distance is 2, but now it becomes 1. So for every edge that we add to the path graph, it actually decrease the distance between 2 particular vertex. So the total distance of this graph G, the winner index of this graph G will actually decrease, since if I put this edge here, then originally it has a distance of 2, but now it has a distance of 1. So it must decrease. And so the path graph Pn is actually the the graph that has the largest number of winner index. So this is part 2. For part 3, so it asks the same question, but now we define G to be a tree. So if you think of a tree for a tree, it has a root. Then I want to keep this the winner index of this graph G to be minimum. Then I want the distance between every two vertex to be as small as possible. Then I don't want to have another layer in this tree. I want to keep all my vertices in this only in this layer, except for this root. So actually, we have a single when a graph has only one layer for n vertices, then it is actually has the smallest. It actually has the smallest number, smallest value of winner index, and this is actually a star graph. So when a tree is a star, the star tree, then we have the smallest value of winner index. Also, actually, it's just called star. So when the tree is a star, we have the smallest value of winner index. And let's calculate the distance between the winner index of a star. So for every leaf and leaf, for every leaf vertices, we have a distance of 2. And for every leaf root vertex, we have a distance of 1. So let's calculate that. Suppose we have n vertices, then we have n minus 1 leaves. And there are n minus 1 edges here. So for n minus 1 edges, we have a distance of 1. And for every leaf vertex, we can choose it by n minus 1, we choose 2. So we from this n minus 1 vertex, we choose 2 of them. So it's n minus 1 choose 2. We have this many leaf pairs, and for each of them, it has a distance of 2. So this is the winner index of the minimum of the minimum. So it is the minimum value of a winner index for a tree. And for the maximum value of winner index for a tree, since a path is also a tree, then we have proven in part 2 that the winner index of G is the maximum when G is a path. So it also holds for part 3. So for part 3, we also have the maximum possible values for winner index of G if G is a path. And this path is also a tree, so this is the answer for part 3. Then for part 9, for problem 9, we have to find a recursive formula Fn to calculate the number of forests with a vertex set n. So a forest is a graph whose every connected component is a tree. Every connected component is a tree. And to do this, I have to first introduce a Cayley's formula. So for every positive integer n, the number of trees on n labeled vertices is this number. So in the solution, I also direct you to a proof of this Cayley's formula. So right now, I'm going to just use this formula. And this is Cayley's formula. For every, so the number of trees on n labeled vertices is n to the power of n minus 2. And this is Cayley's formula. And now suppose, now we want to calculate the number of forests, actually. So suppose we have n vertices. Suppose we have n vertices and a vertex n. So now consider this vertex n. We want to take it along with, so let's first choose k minus 1. Suppose this is k minus 1 vertices. We want to choose this vertex n, and then we form a tree with k vertices. K vertices by adding this n to the tree to this k minus 1 vertices. So we want to have a tree with k vertices. And if you think of the first part, we want to choose this part. So the k minus 1 vertices. How do we choose k minus 1 vertices? We just need to exclude this n. So from the remaining n minus 1, so this is n minus 1 vertices. From the remaining n minus 1 vertices, we have to choose k minus 1 vertices. So this is the number of ways that we can choose these k minus 1 vertices. And by the Cayley's formula, we now have k minus 1 vertices, and then we add this vertex n to these k minus 1 vertices. So by the Cayley's formula, we now have a set of k vertices. So this part. So we want to form a tree. We want to calculate the number of trees in this k vertices. So by the Cayley's formula, we just have k to the power of k minus 2. So this is the formula to calculate the number of ways that we can form trees using these k vertices. And then we have another. So this, for the remaining vertices, is just n minus k. Since we have k vertices here, so we have n minus k vertices here. So the remaining part is n minus k, and we just have to calculate the number of forest in these n minus k vertices. So it's just n minus k. Since fn is the number of forests with n vertices, so we just have n minus k. And then we have to sum for all possible value of k. So this is the formula to calculate the number of forests with a labeled vertex set n. Okay, so finally, part 10, problem 10. For part 1, so Amir is arbitrarily choosing a vertex in the graph to visit, and we call a vertex to be a nice vertex if Amir can visit this vertex with infinite number of times. So it takes infinite number of many steps, and we say that a vertex is nice if it is possible for Amir to visit it an infinite number of times. So if you think of it, if a vertex belongs to a cycle, then we can actually just traverse this cycle for an infinite number of times. And so all the vertices in this cycle is nice. So they are all nice vertices. And actually, we have just directed a cyclic graph. So in a directed acyclic graph, we have no cycle. And since we have no cycle, then for every walk in this graph, we must end it up somewhere that we cannot proceed to another vertex in this directed acyclic graph. So so for this graph, we have no cycles and we have no such nice vertex. For part 2, we have to design an algorithm that, given the graph G as its input, we have to output the list of all nice vertices. So, so as I mentioned, if a graph, if it contains a cycle, then all the vertices in this cycle is nice. And I want to introduce another idea. It's called the strongly connected component. So a strongly connected component in a directed graph is just a component such that we can reach from every vertex to every other vertex. So in a strongly connected component, we can visit. So we can visit from here to here, and then to every other vertex. So if you arrive at a vertex, then you can be sure that you can visit every other vertex, and all. So by this definition, you can see that all the vertices in this strongly connected components is actually nice, since we can visit all other vertex. Then after we visit the next vertex, we can also from this vertex visit back to your original vertex. So we just need to find the strongly connected components containing vertex 1. The strongly connected component containing vertex 1 is actually all the nice vertices that we have. So to do this, we can use Kossaraju's algorithm. You can use Kossaraju's algorithm, and I will, in the solution, I will give you the detail of this algorithm. I'm not going to go through you for this with this algorithm right now. So if you find the strongly connected components containing vertex 1, then this strongly connected component is actually all the nice vertices, since we can reach from the vertex 1 to every other vertex in this strongly connected component. And then we can, again, from that vertex to every other vertex, we can also visit all of them. And for part 3, for a graph, there are some vertices that are not nice, and the TAs want to add the minimum number of edges to those vertex that is not nice, so that the whole graph is nice. The whole graph, every vertex in the whole graph is nice. So to do this, we can also use the Kossaraju's algorithm. So the Kossaraju's algorithm can actually identify all of the strongly connected components in a graph. And so suppose it finds strongly connecting components 1, 2, and 3, and so on to n. And we just need to find for those vertex that is not in any strongly connected components. So in the vertex set, we exclude the union of all the strongly connected components. We exclude all of these vertices, and the remaining vertices does not belong to any strongly connected components. So now, for those vertices, since for those vertices it must belongs to some path, right? So a single vertex is a path with length 1, and let me illustrate with graph maybe. So given a whole graph, then we have several strongly connected components, and then we may have some vertices that is not in any strongly connected components. For example, this is not a strongly connected component, and this is also not a strongly connected component. Then for this vertex, we can actually just add an edge to an arbitrarily strongly connected component, and then from every arbitrarily select a vertex here to connect to it, and then connect it back. Since now from this vertex, you can visit this vertex. Visit this vertex. And then from this vertex, we can visit every other vertex. And from every other vertex, we can visit back here to this vertex. And from this vertex, we can also visit back here. So now, actually, this whole component becomes one single strongly connected component. And we add two edges to, we just need to add these two edges. And for this part, with this, these vertices, we just need to have a vertex. We just need to direct the tail of this path to the head of this path. So I create an edge here. I direct a path, this vertex from this vertex to this vertex, and you can see that this these vertices now actually becomes another strong connected component. So we only need to add one edge for this. In this condition, we only need to add one edge, and we have another strongly connected component. So the whole graph now becomes strongly connected. So the whole graph now, every vertex in this graph is a nice vertex, since they all belongs to some they all belong to one strongly connected component. So this is for this part.